So we're going to continue our conversation with entropy from yesterday. One of the things we did end up talking about was another way to calculate what our entropy was. I'll remind you that that involved using tabulated values to get our total products, subtracting our total reactants, and making sure we are using our coefficients. Those values come from the end of your book in one of those appendices in order to do this particular method. Another thing we can look at, and we're leading towards what we call Gibbs free energy, which is the second new concept in this particular chapter. That's going to involve assuming that at a constant pressure, that the total heat that is going to be involved in a system, not necessarily from the surroundings or to the surroundings, but the total heat involved in a specific system comes from that delta H value that we've talked about in the past, aka the enthalpy value. Again, similar way of calculating that involves using that same method we introduced yesterday. So if you have to, you can calculate delta H values and delta S values. The cool thing is they're on the exact same table. So in the back of your book, in whatever appendix it is, there is a way for you to calculate both delta H standard values, that's what that little knot means, and delta S standard values in order to calculate the total amount of heat or the total entropy that is released to the surroundings. This particular method deals more with our surroundings than it does with our system, but in this case, you have to know how much heat is being released by your system in order to determine what kind of entropy is involved by the or in the surroundings. Okay. One thing to note is that this is in particular going to happen at one temperature. Okay, so this is temperature specific. Whatever that temperature is must be known, and it must be constant. That's what that term isothermal implies. Okay. One thing to remember, we talked about this yesterday, is that the total entropy of the universe must always be increasing. Right? That means we take the entropy from a system and the entropy from the surroundings, we add them together. Their total entropy must be greater than 0. Could one of them be negative and one of them be more positive? Absolutely. But overall, the system and the surroundings added together must equal a positive entropy. Okay? Big concept here, because we are going to be dealing with this on a equilibrium basis, right? We're going to be looking at this on an equation basis for each of our different chemical equations. All right, ready for some fancy looking math? This is a derivation. Please don't panic. Do not write anything on the next slide down because it does not matter until we get to the slide after this. We're going to call this Gibbs free energy here in a little bit, okay? But this is the derivation that tells us why Gibbs free energy is related to the total enthalpy of a system, the temperature the system is at, and the overall change in entropy of just the system. Okay? This is all the derivation that tells us why this is the case. But in what we're seeing here, all I want you to take from it is that we've got enthalpy, we've got entropy, all in the same place. Okay? Our goal here is going to be to look for something that indicates this. Okay? Something that kind of stands in for T delta S of the universe. Is this going to be a number that we can get? Hopefully you're shaking your head no. The total entropy of the universe is not a number we know. Okay? So we have to put this in terms that we can actually understand on a more benchtop level, if you will. Okay? So that's the derivation. What we're going to talk about next is how we're going to use that negative T times that delta S of the universe, this unknown quantity, and we're going to abbreviate it as delta G. That's exactly what's going to happen here. And then we're going to interpret what that value means. So when entropy is positive, like it should be, delta G should be negative. Okay, the number that comes out should be negative. And that tells us, when delta G is negative, that a process is spontaneous. It'll happen without our input. Okay. Big concept here. We're going to take this idea of the entropy of the universe, and we're going to look and see, okay, well, it says negative T delta S. That was from our derivation. So overall, delta G should be negative. And if it comes out negative, that means it obeys that rule of spontaneity. In mathematical form, Gibbs free energy looks exactly like that equation you saw on the bottom, set equal to delta G instead of negative T delta S. I don't want you to panic about what it looks like. I just want you to know what it means. I don't want you to worry about the derivation. I want you to understand that this is what happens. And these, of course, are both the system from that previous slide. Okay? From there, we can interpret what delta G means. Okay, we said, well, if delta G is negative, it means the process is spontaneous. Useful for determining information about a reaction. If we know nothing about the reaction except the enthalpy involved, the entropy involved, and the temperature at which it's being done, we can now determine whether or not it's going to be spontaneous by interpreting that delta G value. Okay? So if delta G is a negative number, of course the forward reaction is then spontaneous. And this is, of course, assuming you are calculating delta H correctly using the methods we talked about in the past, and delta F correctly using the methods we talked about today and yesterday. If our delta G value is at 0, the system's not moving forward or backward. It's kind of at that equilibrium point. And if delta G is positive, the reaction can be assumed to be spontaneous in the reverse direction of the way that you calculated it. So that also means it's not spontaneous in the forward direction. Okay? That first one says when delta G is negative that the reaction is spontaneous in the forward direction. You can make the assumption that it is not spontaneous in the reverse direction as a result. What's going to end up happening here is we're going to see that delta G values can be flipped. Positive and negative indicate spontaneous or not spontaneous. Okay, so now we know how to calculate delta G values, right? If we have a delta H and we have a delta S and we know the temperature of the system. There are other ways to calculate delta G values, and they involve using standard delta G values. So just like we did with our delta S values, we can get values that involve each of the individual reactants and products, and we can calculate the overall delta G. Ben. You're being called.
I'm behind on my notes enough.
Huh?
I'm behind on my notes.
Okay, don't worry, we'll catch up. All right. So we can calculate now a standard delta G using two different methods. This guy is going to be more useful to you than you think because, again, at that table at the back of your book, you've got standard delta H's, you've got standard delta S's, and you've got standard delta G values now. So we can use the same method we were talking about yesterday with delta S's to do the same thing with delta G. What do you need in order to do this? Table, right? Okay. So, Gibbs free energies equation. What do these little things mean? They mean standard. They mean we can get them from tables, right? They mean we can calculate them. We've got a few methods to do this for delta S, right? We talked about a few of them yesterday. We talked about delta S standards. We talked about delta S not standard. We talked about delta S at different temperatures. We talked about a couple of different ways to calculate delta S yesterday. One of the things to note is that this particular version of Gibbs free energy requires the standard values, okay? Now, let's say you're given delta G and delta H. Can you calculate delta S? Theoretically, if you know the temperature, right? So this particular equation works for multiple uses. And one of the things that we're going to see is interpretation of this equation. So if I say you have a positive delta H and you have a negative delta S, okay, what is going to be the sign of delta G, positive or negative? Positive delta H, negative delta S means what about delta G? It's going to be positive. What does that tell you about the reaction? It's spontaneous in the reverse direction of the way it's written. So we're going to be working on interpretation using Gibbs free energies equation. Will we be using numbers at some point? Sure. But understand that there are ways to interpret this without specific numbers. Okay? All right. Don't forget, in the overall delta G free energy equation, One of the terms is enthalpy, that's delta H. One of the terms, negative T delta S, so the whole thing is entropy. The whole thing. Temperature only impacts your entropy in this case. Does it matter at what temperature you're doing this equation for delta H? Not at all. Yes, ma'am? Yes. Enthalpy, entropy. All right, a few more things to look at. So let's do some interpretation. We're just going to look at this. Here we have a table. And instead of giving you numbers, okay, instead of giving you numbers, we're giving you signs, positive, negative, or zero. Really just positive or negative. Okay, so using that delta G equals delta H minus T delta S, we're going to interpret using the signs and determining whether or not the reaction is spontaneous or non-spontaneous, regardless of temperature or if temperature has an impact. Okay, so let's look at this first one. I've got a negative delta H. I've got a positive delta S. So the entropy term, because delta S is positive, is going to be negative, right? Since my delta H was also negative, delta G is automatically going to be what?
Negative.
Negative no matter what, right? That means, what about the reaction?
Spontaneous.
Spontaneous. Does temperature matter? No. Every single temperature, that particular reaction is spontaneous. Okay, let's do the next one. Next one says that our delta H is positive, our delta S is negative. What does that mean about delta G?
Positive.
Positive number. What does that mean about the reaction?
Not spontaneous.
Non-spontaneous. Does the temperature matter? No, it does not. Then we get into the gray area. We get a negative delta H and a negative delta S. Can you see why delta G can be either positive or negative? Okay, good. So that means this reaction might be spontaneous at certain temperatures, but not spontaneous at others. In particular, this one's going to be spontaneous at low temperatures. It's going to be not spontaneous at the higher temperatures. Because the higher your temperature is, the larger this negative term gets, right? This is the way you need to think about Gibbs free energy. What does it mean if a reaction is spontaneous from yesterday?
It happens without our intervention.
Happens without intervention. We don't have to heat it, we don't have to do anything, we just put it together and things happen. Okay? What does it mean if it's not spontaneous? You got to do something to make it happen. Just remember, some of the stuff we talked about yesterday involved the difference between spontaneous and non-spontaneous, irreversible and reversible. Don't forget that stuff. Last thing. The last thing we're going to talk about with Gibbs free energy. When we are at equilibrium, we can calculate a delta G using a standard delta G. Remember, these two things are not the same. One of these we can use the table values in the back. This particular equation allows you to determine what the free energy is at different temperatures. Okay? What is Q? Ooh. Oh. You remember K?
It's always confused me. Which K is this? Uppercase?
Uppercase K, yep.
Oh, no.
We're talking about equilibrium, right? So what's Q? Q is like the photograph at any time. Remember? K is what it is supposed to be. Q is what it's not quite at yet. Remember that Q is our comparison tool. So when we had K values, we calculated them using products over reactants. Remember that? How do we calculate Q? Same exact way. The difference was K is at equilibrium. Q is before. Well, Q is are we at equilibrium? Q is the question mark. Q is, are we at equilibrium? Are we going to have to shift to the left to get to equilibrium? Are we going to have to shift to the right to get to equilibrium? This is called the Nernst equation. Nernst. Okay? At equilibrium, we know that Q should be K. Remember that? We had Q greater than 1, and we had Q less than 1. When Q is greater than 1, what did that mean? That we had more products than we should, so we had to shift this to the right to get to equilibrium. When Q is less than 1, we had more reactants than products, so we had to shift left to get to equilibrium. But when Q was equal to K, we were at equilibrium. Okay? So just remember some of those concepts. This becomes this guy. To calculate a delta G standard, all we need is a K value and a temperature. Could we get a K value very easily? If we know the concentrations or the molarities that we're dealing with? Mm-hmm. Absolutely. So you're going to have to put some of those concepts from the last 4 chapters we've covered over equilibrium kinetics to help you here. Okay? Last equation in this particular chapter is the Nernst equation. And the rearrangement of the Nernst equation. Why would we rearrange it? What are we solving for here? K. In this particular case, what would I need to know? I need to know the standard delta G, so I'd probably have to use a table in the back of the book. And what else? Temperature. R is a constant, remember? So if I want to solve for the standard enthalpy or the standard, Gibbs free energy, I can, using temperature and the equilibrium constant, so K. Or I can calculate K, the equilibrium constant, using that standard Gibbs free energy and temperature. Yes, ma'am?
What would be E?
That's E2 though, like a natural log. So you know the inverse of the natural log? Yeah. Good question. Any other questions? We good? Okay. All right, we're going to stop there.